In this video, I introduce a minimum description length principle for neural network training. Neural networks trained in a supervised fashion can generalize where to new data if information in the width is much less than in the output vectors of the training cases. Insufficient training data makes complex models overfitting, which makes the model worse at fitting new data. To avoid model overfitting, supervised neural network training is to penalize the amount of information contained in the model parameters. The minimum description length principle asserts that the best model of some data is the one that minimizes the combined cost of describing the model and describing the misfit between the model and the data. For supervised neural networks with predetermined architecture, the model cost is the number of bits it takes to describe the width, and the data misfit cost is the number of bits it takes to describe the discrepancy between the ground truth and the prediction of the neural network on each training case. Here is a neural network, this input, this output, and this weights. Minimum description length principle carry out two steps. First, minimize the model cost. Second, minimize the data misfit cost. To apply the MDL principle in neural network training, a code scheme is required to measure the data misfits and the model weights. Suppose the probability mass P delta Y is assigned to each data misfit delta Y. The data misfit is coded using negative log P delta Y bits. The goal is to minimize the expected number of bits, namely, the prediction DGC tends close to the ground truth YGC on each training case C. Suppose the data misfits are sampled from a zero-mean Gaussian distribution with standard deviation sigma j. The probability mass of a data misfit is defined as here and explained in this figure. Description length of the misfit is written as here, which includes 4 terms. To minimize the description length summed over all n training cases, the optimum value of sigma j is the raw mean square deviation of the data misfits from 0, namely the sigma j is the value of this formulation. Substituting sigma j into the description length, negative log p, and summing over all n training cases, the last 2 terms in the description length become constant, and data misfit cost, as shown here, as the last 2 terms, and this constant, this data misfit cost. Where k is a constant that depends on only t, the description length is minimized by minimizing the Euro square error function, as shown here. Assuming that the model weights are finally quantized and also come from a zero mean Gaussian distribution with the standard deviation sigma w that is fixed in advance. The description length of the weight is proportional to the sum of model width squares, as shown here. The total description length of data misfits and model width is minimized this formulation C, which is the same as the standard weight decay method. For more details, please check with these references. Thank you. Bye.